Hello, everyone. I want to welcome you to today's presentation of the ONF Spotlight series. So I want to introduce myself first. My name is Mahir Gunyel. I'm working at Netsia as Senior Architect. I have been working in telecom software sector for more than 20 years. And I'm also TST member of the Volta SEBA project. I'm also today the moderator of this presentation. It's my pleasure to have Carmelo, Craig, and Mario today. They're going to talk about Tassen, which is a next generation BNG control plane user plane separation API. Great to have you guys. Now I want to hand over to you to inform yourself and do your presentation. I think we'll start with you, Mario.
Yeah, thank you, Mahir. My name is Mario Kind. I'm with the Deutsche Telekom. I have a very long experience since 15 years on various networking topics and SDN, NFV as well. And I've been quite on application side, always quite close to the BNG. And I'm happy to be here and to present our ideas. I think Carmelo, it's your turn.
Next. So my name is Carmelo Cascone. I've been with ONF for 2 years. I'm a software engineer. And since I joined ONF, I've been focusing on using programmable hardware and technologies like P4 to deliver on some of the ONF solutions for both broadband access, mobile access. So I've been working on projects related to BNG disaggregation and now also to UPF disaggregation. And like Mario, I'm very happy to be here and present this Tassen work that we'll be working on. I guess Mario, Craig next.
Hi, it's Craig Stevens here from Dell. I work in the Integrated Products and Solutions CTO team. It's quite a mouthful, but one of the things we've been working on, I've been focused on, I guess, in the last few years is the Stratum team. I'm one of the TSTs there and a fairly active member and contributor. And I guess, through that work, we've been doing a lot of work on network function offload, and BNG is one of those use cases. So happy to be here today, and I think you'll find this is pretty interesting. Back to you, Mario.
Thank you, Craig. So, let's get started. I will take the first part and speak about the motivation that we at DT and others in the operators have to look into this and try to explain what are we going to do. So I'm working in a Deutsche Telekom project called Access 4.0, which is a huge program which focuses on our access networks and wants to transform them from the current design, which is a more telco-oriented style, to the new ONF-enabled, SDN-enabled broadband access architecture. We are focusing on the access network, so I have multiple services in focus. And we are looking here into the edge of our networks, which are the central offices, huge housing spaces with lots of space, cooling, etc. And we are looking specifically also in this project, beside the access network technologies, into the BNG, which is our anchor point for connecting customers with our backbone. The project itself looks quite heavily into openness and for extensions to be future-proof and to enable flexibility that we believe we will need in the future with coming new use cases like 5G, like edge computing, etc. Already in the project, we are on the way to disaggregate our current BNG from a black box to a device which is separated between hardware and software. And we look there also into new ways to find hardware. More specifically, we have looked into open source hardware based on the Open Compute project, and we have developed here an BNG device which is called Magenta Switch and will be available later this year. Still, one of the things is that the software we are in a disaggregated BNG is a big block which is running on the device, and this has certain drawbacks. And here's the point where the control and user plane separation comes into the focus. Carmelo, can you please walk to the next slide? Thanks. So our basic idea is to take this big software block and put it into pieces, into a BNG control plane, into a BNG user plane. The user plane runs on the device and on top of the hardware and provides functionality to attach to the control plane, get management, etc. We will show more details later. Why are we doing this? This is very important stuff for us as operators, is to scale all the things independently, depending on our use case and depending on the change of services, etc. And we hope that with CUPS we can enable new ways of redundancy and have better and fewer outages of our software stacks. The other thing is that we hope to do is to have independent life cycles of the control plane and the user plane, and last but not least, to mix and match different hardware types under the same control plane. So not necessarily limited to, for example, an classical telco chipset, or use upcoming native FPGAs, or use whatever else exists. And also here we will speak later in our talk about the options and what is in focus of our work. So the question is how to enable these new APIs. There is a proposal already discussed by the Broadband Forum, which is the main organization where all the functionalities around BNG, subscriber management, etc. are defined and architectures developed. And they have a initial proposal which is called PFCP, which is a protocol from the mobile world used there to separate between the control and user plane. As I said, one of the main motivations of our Access 4.0 project is to look into alternatives, look for innovation, existing approaches, and there is one that comes from the ONF, and this is heavily cloud and data center inspired approach, that is the use of P4 and GNMI. And this is where our talk is about, how this alternative to the PFCP based on P4 and GNMI is working and what our idea is. Carmelo, I think it's your turn.
All right, thanks, Mario. So in the next slides, I'm going to introduce this, this idea behind Tassen. And before I do that, it's useful to visualize what BNG disaggregation looks like. So a BNG is essentially a specialized router. And so following the SDN paradigm, we can, as Mario described, we can split this box into two entities, a control plane and a user plane. The control plane is where we have all the intelligence. So think of the routing protocols, authentication, accounting, etc. Well, the user plane is where the actual packet processing happens, and especially high-speed packet processing. So when implementing the control plane, usually the choice is around the programming language that one wants to use, or the architecture, whether it's a microservice-based architecture or a monolithic component. When it comes to the user plane, the choice is instead around the type of merchant silicon and the port configuration. So whether it's a switch-like box with many ports, or a smart NIC, which is a few ports, whether it's a single chip or dual chip solution, whether it's based on switching ASICs or FPGAs, or perhaps a combination of both. The goal of this talk is not to discuss the merits of the different options. Indeed, operators have reason for wanting, this optionality to be preserved. So the goal of this talk is to discuss what we think is the right API between control plane and user plane, an API that truly provides silicon independence and facilitates interoperability between control plane and user plane. Now, there's a problem here, and the problem is that all these different options, they all provide equivalent features in terms of routing, PPU termination, Q&Q, lawful intercept, etc. But they fundamentally have different pipelines. And this is a known problem with what we call SDN version 1 and OpenFlow. Indeed, in existing production deployments of OpenFlow, the problem is that there's a tight coupling between the control plane and the user plane pipeline. So the specific tables and other things which you'll find in a pipeline of the specific silicon vendor that an operator has chose to use. So operators invest a lot of time and resources in implementing this control plane for the specific silicon vendors and pipelines, and they realize that when they have to move to a different silicon vendors, they essentially have to spend the same amount of time and resources as the first time. So we think that the same problem applies to the BNG case, and we think that we can solve this problem using the next-gen SDN approach. So the way of doing that is by formally defining a common pipeline. So a pipeline that is common to the different user plane options. And in Tassen, we abstract this pipeline with a logical three-stage model. So our Tassen pipeline has an ingress pipe, a traffic manager, where we find all the hierarchical QoS processing, and an egress pipe. The ingress pipe is where we have match action tables for upstream and downstream processing, things of PPU termination, routing tables, as well as the counters for accounting purposes, QoS classification, etc. The traffic manager is where we have all the queues, as well as the different levels of scheduling required for HQoS. And finally, if a packet is not dropped by the HQoS module and makes it through, it will be processed by an egress pipe, where we have things like post-QoS counters, etc. So the idea behind Tassen is that we can use languages like P4 to formally specify and so provide a very precise bit level specification of how packets should be processed across this pipeline. For the HQoS part, the idea is that we can use Yang to model the configuration state of an HQoS model. So think of setting the scheduling hierarchy, setting the scheduling policies, and all of that. So once we have this model, we can then use APIs like P4Runtime and GNMI to manipulate the pipeline state at runtime. So P4Runtime can be used to, for example, read and write table entries, the same tables defined in the P4 program. While GNMI can be used to, for example, set and get the, again, scheduling hierarchy, the scheduling policy, shipping rates, etc. These APIs are what we call next-gen SDN APIs, because they represent an evolution over the first generation of SDN. So think of OpenFlow, NetConf, and other APIs. They're essentially very generic model-independent interfaces that allow to manipulate state-defining models using P4 or Yang. They're designed with performance in mind, and also they're very easy to implement in many different programming languages because they're based on gRPC. So the goal in Tassen is to provide a new logical P4 program that defines this, formally defines this pipeline. And we're also looking into reusing some of the existing Yang models for QoS from the open config. So the idea is to reuse the model, or perhaps extend the model if it doesn't satisfy the BNG requirements. So I mentioned this term logical P4 program and logical pipeline. So what do we mean by that? The idea of a logical P4 program is a P4 program that abstracts commonality between all the different physical pipelines. So to give you an example, in Tassen, we have this P4 program that we use to define a few tables that look like a database for storing things like bill and tags, PPA session IDs, routes, etc. When it comes to the physical pipeline, here we have, again, different pipelines that all provide equivalent forwarding behavior, but they have different table structure because of the different hardware constraints. So, for example, for Tufino, when writing a P4 program for Tufino, usually we have to split what is a logical table into multiple tables. And we do that usually for optimizing memory resource allocation between TCAMs and SRAM. We do the same for FPGA, so usually we end up with a slightly different design that optimize at different goals. In the case of FPGA is usually, for example, the placement process of the FPGA compilation, and we can think of other optimization, for example, for silicon use in the magenta switch. So at the end of the day, we have one logical pipeline and different physical pipelines that they all do the same things, but they look different. So the idea behind Tassen is that the BNG control plane can operate against the logical pipeline. The BNG control plane writes P4Runtime entries for the database-like tables. And then the BNG user plane is responsible of doing what we call P4Runtime translation. So translating P4Runtime entries for the logical tables to the physical tables. And the cool thing is that this translation can be either manual or automated. And when I say automated, I mean, if both the logical pipeline and the physical pipelines are defined using P4, there is already some exciting research about automatically generating the translation logic between the two. Another cool benefit of using P4 is that we can validate the logical pipeline and the derived P4Runtime API using some packet-based unit tests. So the idea is that we can take a software switch like BMV2, load this with the logical P4 program, and then we can write functional tests. This functional test will emulate things like setting up a PPU termination from the BNG control plane, and so we can produce an input packet and verify that the output is what we expect. For example, the PPUE and VLAN headers have been added or removed to the packet depending on the direction of traffic. We can also simulate things like punting control plane packets, as well as accounting, etc. But most importantly, once we have this test, the same test can be used as a reference for control plane and user plane implementers. So for example, a vendor of a BNG control plane can use the same software switch and logical pipeline to test their implementation, while a user plane vendor can use the same test we use with the logical pipeline to test their physical pipeline implementation. What is more is that because we're using a formal description of the pipeline, we can use techniques like P4 program analysis or symbolic execution to do FATS testing. And FATS testing is very useful to, for example, discover hard to catch bugs in the physical pipeline implementation that otherwise we will never notice if not in production. And this is already possible. Indeed, there is already some research and open source tools that allows one to automatically generate test cases given a description of a P4 program. And also it's worth noting that Google uses the same approach. So describing their switch pipeline in P4 to validate the switches of their data center, the data centers. So, this is the high-level description of Tassen. In terms of project status, we have a brigade that counts 5 members, not just myself, Mahir and Craig, but also Daniela and Ralph. We have some initial code on GitHub. This has been the main output of this brigade. We've been meeting bi-weekly since March 2020. And this GitHub repo already contains an implementation of the logical P4 pipeline. We have a P4 program we call BNG-UP that provides a description of the downstream and upstream processing for both PPPoE and IPoE, as well as accounting. We have an initial collection of functional tests. We use a Python-based framework called PPF, Packet Test Framework. And we also have a reference implementation of this P4Runtime translation logic. We call this tool Mapper. It's a tool written in Golang that has a P4Runtime northbound and southbound, and already supports translating entries from the logical pipeline to the ONF Fabric.P4 program. But it has also an extensible architecture that should allow anyone to add support for other pipelines. So this was the overview of the Tassen project. And now I'll leave it to Greg, who's going to talk about the relationship between Tassen and PFCP.
Great. Thanks, Carmelo. I thought we'd just start off with this diagram that's actually, I've taken it from the Broadband Forum WT459 specification, which is actually the disaggregated BNG architecture. So when we talk about PFCP, and Mario mentioned it earlier in the talk, it's one of the protocols used. If you look in the middle of that screen, you'll see that the DBNG control plane function block is on the top of the diagram. The DBNG user plane function block is the bottom part of the diagram. And there's several interfaces: the management interface, the control packet redirect interface, and the state control interface. And PFCP is actually the protocol being used for the state control interface. However, you know, as I think we've mentioned a couple of times here, it's a protocol that was originally developed for 3GPP components, and so requires some fairly intensive extensions in order for that to work with BNG. It's sort of open flow like. It's a fairly heavyweight sort of protocol. And I guess in terms of the actual forwarding pipeline, it's a little bit ambiguous in that there's the specification. Obviously, there's a lot of English and diagrams and figures, but the actual implementations to date, are more vendor specific, and so that's probably going to take time. If you look at some of the other components that have happened in 3GPP, it's probably going to take time for that to evolve over time. And I guess the other part of it is that we're not using cloud native type of API. So I guess we looked at this, thought about the problem, and really what we're seeing, Carmelo, if you can go to the next slide, is that what we're really looking at is we're trying to learn from our OpenFlow experiences, obviously using a cloud native API like gRPC, but really focusing in on the forwarding pipeline and getting a formal specification of that forwarding pipeline so that we can fully test it. As Carmelo had run through at a high level, there's a whole pile of testing framework that we can wrap around this so that we can test not only the user plane part, but the control plane part of the components. And what we're seeing is that the hardware, like the actual hardware, whether it's a switch or a SmartNIC, is exploding. And so that's really the focus, is how can we enable service providers to be able to onboard this hardware very easily in an easily testable and agile method, I guess. And so there's two ways that I guess we've thought about this. Obviously, a BNG could implement the Tassen APIs, the P4Runtime and GNMI API interfaces natively. And so that's what we're showing on the diagram here. And then the second, the second option, I guess, which Carmelo has just rolled out there, is for the, we don't want to. It's not an either or. If you had a vendor that's doing a broadband forum BNG, they can still interface that into the Tassen APIs, similar to this diagram here, where they use PFCP between the control plane and user plane. And then we break the user plane up basically into, you can see what we've called it there, the DBNG-UP-C. So a control plane part of the user plane, if you like, similar to what we've done in the UPF for programmable pipelines, where we break the user plane up into two parts. There's effectively a control plane part of it that sits above the APIs, above Tassen, and uses P4Runtime and GNMI to program the lower level pipeline that's sitting down there as the BNG-U. So I've named them differently, BNG-U and BNG-C for the Tassen side, and DBNG, UP and CP, just so that you can see the difference between broadband forum and the Tassen APIs, but you know, I think you can basically coexist both architectures. So Carmelo, that's I guess back to you for a summary. And
yeah, so to conclude, we know that BNG disaggregation is an essential part of the SEBA vision. So exactly like Volta, we also need to disaggregate the BNG black box, you know, to be able to truly apply the benefits of disaggregation and virtualization for broadband. We realize that when doing so, when applying the CUPS architecture, there is an interoperability problem. Of course, we can come up with APIs, but really this API to be successful needs to make the interoperability part painless, right? An operator should be able to mix and match user plane and control plane implementation, you know, without investing a lot of money and years in development. And so we think we can achieve that by using P4 to formally specify the logical pipeline and by writing tests against it. So essentially, we are working on a specification that really thrives in code rather than words and figures. And also the other part of it is that there is a lot of research that is coming out that, for example, allows us to do what I described before, this automated P4Runtime translation that has strong guarantees that this translation is and provides the desired forwarding behavior. We can do FOTS testing to really improve our user plane implementation. We can also do verification. This is something I haven't talked about, to make sure our pipeline it's well defined and doesn't violate any for example operator defined policy. There's something else we didn't talk about, which is the fact that this idea Tassen can be used with or without SEBA. So when used with SEBA, the idea is that you can imagine an application running on top of ONOS next to the Volt application and Trellis application. We call this the Tassen app, which provides the P4Runtime and GNMI endpoints that a control plane can use. If used without SEBA, then we can imagine having sort of a standalone software components that does the P4Runtime translation as Greg was showing in the slide before. And also clearly, I mean, since this all idea started by looking at PFCP, and PFCP is a 3GPP defined protocol, and ONF is also heavily invested in the mobile space. We're also currently exploring the same approach for the 5G UPF. What we're doing there is we're using P4 to model the logical UPF pipeline for things like GTP termination and other stuff. And then we're using that as the common API between different implementation of the UPF, so both hardware-based implementation, but also software-based implementation. Last slides. In terms of next steps, so we plan to keep this brigade meetings on. We have a bit more work to do. So we want to continue modeling more pipeline capabilities. So things like multicast, local intercept, wholesale tunnel relay, etc. We talked about using OpenConfig to model the QoS part. So what we need to do is really try out those models and understand if those can satisfy the requirements of a BNG for multi-level scheduling. If not, either extend the models or create a new one. It will be interesting to implement the reference P4Runtime translation for more targets, for example, the Magenta switch, but also the Smart Naked option or the Fino Plus FPGA, or even software-based vBNG. We talked about FOTS testing, so we would like to use an existing open source tool called P4 Package Gen to actually automatically generate this test cases, and there's much more. I guess the bottom line is that this is a brigade effort, so if you're interested and would like to join the effort, you're welcome to do so. And in this case, you can reach out to me, and I'll be happy to invite you to the brigade meetings. And with this, I conclude the presentation, and I think we can take some questions.
Okay, thank you. I have a few questions. First of all, Carmelo, because you're using P4 runtime for control and user plane separation API. What are the drawbacks of using P4Runtime rather than custom API? Would you rather to use a custom high layer API or not?
Yeah, so it's not really an issue, but the fact is that P4Runtime gives you an API that's based on the same P4 program, right? Which is quite a low-level description of the pipeline. It's a precise and unambiguous description. So if you understand the P4 program, then you understand how to program tables. But I will say one of the drawbacks of using P4 is that I'll give you this example. We have in the logical P4 program, we define both downstream and upstream processing, and in both places, so both pipelines, we have pretty much the same table that at least contain the same data. So we have tables that match, for example, on the IP destination address, and they use to set things like PPA session ID and VLANs. This is for the downstream. And for upstream, we do the same, but the table is inverted. So we match on things like VLAN IDs, and we do anti-spoofing. So one of the downside is by using this low-level representation, the API it's a bit inefficient. A control plane, like in this case, have to write twice the same information for downstream and upstream, while at the end of the day, subscribers have the same identifiers in both directions, right? But I also think this is a minor drawbacks, I guess, compared to the benefit of truly understanding what's going on with the packets in the pipeline.
Okay. And how does Tassen account for difference between different BNG deployments? Like some deployments have PPPoE, some of them have IPoE. Some BNGs are already perhaps distributed a bit by the operator. So how does Tassen account between them?
Yeah, this is a good question. So when we start working on this, we realized that, for example, we started meeting myself and Mario, right? So Mario Deutsche Telekom, and at ONF I was working on SDBNG, and both we were targeting PPPoE-based service delivery. And so we started designing this pipeline. And then Craig joined. Craig was working on a different implementation that instead targets IPoE-based service delivery. So this is tricky. So right now, if you look at the code, we have two branches, one for PPPoE and one for IPoE, and we're trying to figure out if it makes sense to merge the two, sort of have a common pipeline that does both, for example, PPoE and IPoE. This is one option. I think one other, perfectly fine option is that where Tassen maintains a collection of P4 programs. We can think of a P4 program for PPoE, one for IPoE, or you can even think of Tassen as the place where, Deutsche Telekom formally specify the pipeline it requires, or Turk Telekom does the same, but for their networks, and AT&T and other ONF operators do the same. Yeah, so I don't know if Mario, Craig, you guys can add something to that.
Yeah, so I think you kind of mentioned we've got that separate branch for IPoE at the moment. That branch actually does integrate both PPoE and IPoE. So I think it's definitely doable, but you're right, we have the option to do either. And that's just one example. There's probably others around, whether it's MPLS or SRV, SRV6, or maybe even SIM6, or what are the different types of encapsulation. I guess one of the beauties of the way you've formulated the mapper is that we can have these different logical targets that then get mapped to the physical targets. We're not just specifying one logical target, so that can change over time. We can also have parallel versions of those.
Thanks. The next question is just about SDNization and control plane separation from the user plane. In current SDN solutions, there is a risk to carry a lot of traffic to control plane. When you separated the control plane from the user plane, there's a risk to carry a lot of traffic to control plane to assure the control. So do you see this kind of risk in BNG separation in Tassen, for example?
Yes, this risk exists. It's especially an issue if you think about geographically separated control plane and user planes. Practically, we are trying it in the SEBA design, and we have different options where we can use, for example, also the normal data, the normal management and fabric of SEBA to use this, and then the bandwidth we are speaking about shouldn't be any problem anymore. On the other side, for geographically distributed solutions, this is quite a difficult task. Having this flexibility with more fine granular description, what we want and how we could describe it with P4 or with GNMI, there might be options also to differentiate between state which needs to be updated in a short term than in a longer term. For example, for accounting, we might use systems where we can have for things that we still have to count on a timing or volume based, more fine granular counters and reports than we have, for example, for flat rates, which is something where we have at least some problems today in our models to describe it. This might help in the end. But yes, that risk exists, and it's most probably hard to tackle right away from the implementation point of view. There's also the deployment that you have to take into account.
Yeah. There's also a similar risk for the other switch resources like flows, the queues, schedulers, etc. Especially if you want to give services per users, and you have to create a lot of queues, schedulers, or have to push a lot of logs to switch. So
yeah.
Do you experience any of these problems when working in Tassen?
Well, Carmelo, I'm not aware that we have experienced it so far, right?
Well, I can attempt an answer, which is, I mean, this is a problem that again affects implementation, right? So there's known, like the main difference between using a switching ASIC versus an FPGA,
yes.
or some other target to implement the user plane is that switching ASICs are very fast, but they have small memories, and it's hard to feed a lot of subscribers, or a lot. It's an arbitrary definition. While FPGAs and software-based processors are a bit slower, but they can use external memories, all of that. So I mean, in terms of Tassen API, I guess the way this will work is that, I mean, the control plane shouldn't care about all these details, right? So the control plane works against the logical pipelines, against the logical table, and then whether we map those logical tables into highly optimized tables, or even different pieces of hardware. Like I mentioned before, the ONF is trying to use the same approach for UPF. In that case, we're targeting an implementation that has both Tofino ASIC as well as FPGAs, as well as software-based processing, and we move sessions between the hardware fastpath and the software fastpath based on the throughput and QoS requirements. But the beauty of the approach is that the control plane doesn't know anything about it. It's writing against the logical pipeline that at eye level models what could happen to packet. But then internally, we can take decisions on, for example, where to allocate a sessions, whether to do it on the switching ASIC or the FPGA, and program all the necessary forwarding rules to to shuffle packets around in a way that makes sense, that from the perspective of the logical pipeline, always produces the same input and output. So I guess in general, the short answer is that when designing this API testing, we should be aware of these issues, but also make sure to design an API that is transparent of the, I would say, different solutions we can adopt to scale the data. I don't know if Craig wants to.
Yeah, so I'm probably going to say, I'll just add to that. I mean, we've done a fair bit of work on running Stratum on top of FPGA, and we've found that using the BNG control plane, we've set it up for 20,000 subscribers, and we've been using, I mean, that equates to like 80,000 queues and probably as much as maybe even 100,000 different rules. And we've been, performance testing that, and that seems to be scaling quite well. Really the whole point of this is that the control plane doesn't really receive the data plane traffic, obviously. It's really just for new subscriber setup. So that's really, the testing we've been doing is, can we do that? And we think we're at 20,000 subscribers now. We think we can scale that to 100,000, and that's per card, and we can actually fit a couple of those in a server, and then you can actually even aggregate several servers. So, there's obviously a way to go to get to that full large scale, but definitely for a small pop, that's no problem, and it'll be interesting to see how far that scales.
I want to add something more, which is the fact that we're using P4Runtime. It's helpful because P4Runtime really was, as an API, was designed with these issues in mind, not just data plane scalability, but before you mentioned this problem of distributing the load. I mean, there's a solution to the problem that of distributing the load to multiple control planes. Now, P4Runtime, it's a fairly simple, but also quite advanced API. For example, allows these things where we have multiple control planes controlling the same device. It provides efficient batching mechanism where you can batch a lot of entries in one message and do those things. So in general, I think that overall the API and the technology we decide to use to implement this API should be able to, to support the scale requirements.
Okay, thank you guys. If you don't have any last comments, I want to thank you for the great presentation. It was really mind-opening. Thank you to all.
Thanks, man.
Thank you.